Hi students, in this class we are going to solve a numerical problem on short transmission line. We have an overhead three-phase transmission line. The receiving end power is 5000 kilowatt. The receiving end voltage is 22 kilovolt. Power factor is 0.8 lagging. The resistance of the line is 4 ohm. The reactance is 6 ohm. We need to find out the sending end parameters. When you look at this operating voltage, let's look at the classification. When the operating voltage is less than 20 kilovolt, we call it short transmission line. When the length is between 20 and 100 kilovolt, this is medium line. But here, when you look at the operating voltage, it is 22 kilovolt. This is more than the voltage specified for the short transmission line. But here, the value of capacitance is not given, and only for short transmission lines we need not to have the capacitance value, because we neglect the effect of capacitance only in the case of short transmission line. As the capacitance is not given in the problem, it is clear that this is a short transmission line, irrespective of a slight increase in value of operating voltage. This is the equivalent circuit of short transmission line. This is the load parameters. Here the resistance is equal to 4 ohm and the inductive reactance is given as 6 ohm. So it is J6 ohm. Now let us write the receiving end voltage. The voltage is given, this is equal to 22 kilovolt, that is 22,000 volt. The voltage given in the problem is the line value. We need to write the phase voltage. We assume that it is a star connected system, so the line voltage is equal to √3 times the phase voltage. So here phase voltage is equal to the line voltage divided by √3. So this is equal to 12,701 volt. This is the magnitude of receiving and phase voltage. We have to write all the values in phasor form or in the vector form. So VR is equal to 12,701 plus J0. The imaginary part is 0 because this is taken as the reference vector. VR is our reference vector. So it is equal to 12,701 plus J0. Now we will find out the current flowing through the line. The current is same both at the sending end and at the receiving end because all elements are in series. As you know, P is equal to √3 into VL IL cos phi. This is the formula to find out power in the three-phase load. So IL is equal to P divided by √3 VL cos phi. Here the power is equal to 5000 kilowatts divided by √3 into the voltage is 22 kilovolt into power factor is 0.8. The current is equal to 164 amperes. This is the line current at the receiving end. We have to find out the phase current at the receiving end. In the star connector system, as you know, the line current is same as the phase current. So the receiving end phase current is also equal to 164 amperes. But now we need to write this current in the vector form. As you know, in the vector form, it is equal to magnitude of the current into cos theta plus j sin theta. Here it is cos phi r plus j sin phi r. So IR equals, here phi r is equal to, from this power factor we can find out the receiving end phase angle. It is equal to 36.86 degrees. As the load is lagging power factor nature, you have to give minus sign. So it is equal to 164 into cos minus 36.86 plus j sine minus 36.86. So this is equal to 164 into cos of minus theta is cos theta, sine of minus theta is minus sine theta. This is equal to 131.2 minus J 98.4 amperes. This is the current flowing through the line. It is 131.2 minus J 98.4 amperes. Now we will find out the sending end voltage. The sending end voltage equals the receiving end voltage plus the line drop. So Vs equals Vr plus the line drop is current into the impedance. This is equal to the receiving end voltage 12701 plus J0 plus the current is 131.2 minus J 98.4 into the impedance is 4 plus J6. The sending end voltage equals 13,816 plus J 393.6. In the polar form, this is equal to 13,821 angle 1.63 degrees. So the sending end voltage is 13,806 plus J 393.6 volt. The polar form, it is 13821 angle 1.63 degrees. This is our sending end voltage. This current can be written in the polar form. This value in the polar form is 164 angle minus 36.86 degrees. Here both voltage, sending end voltage and current are written in the polar form because we need to find out the phase angle between these two, from which we can find out the sending end power factor. The sending end phase angle is equal to angle between Vs and Is. What is the phase angle of Vs? It is 1.63 minus the angle of sending end current, which is same as the receiving end current, minus 36.86. So this is equal to 38.49 degrees. From this we can find out the sending end power factor. It is equal to 0.78. So cos phi s equals 0.78. What is the receiving end power factor? It is given in the problem. This is 0.8. Now we will find out the regulation. Regulation equals the sending end voltage minus the receiving end voltage divided by the receiving end voltage. Here you have to write the magnitudes only. Either you can use the line voltage or the phase voltage. If you use the phase voltage for both sending end and the receiving end voltage, you should use the phase values. If it is line value, for both Vs and Vr, you should use the line value. Let's use the phase quantities here. The sending end voltage is 13821 minus the receiving end voltage is 12701 divided by 12701. This is equal to 8.8%. You should know this can also be written as 12701 angle 0 because this is the reference quantity. So regulation is equal to 8.8%. Now let us find out the transmission efficiency. The transmission efficiency equals output power or the receiving end power divided by the input power or the sending end power. The sending end power equals 3 into Vs Is cos phi. It is 3 times the phase power at the sending end. These are phase quantities. So this is equal to 3 into Vs equals 13821 into Is equals 164. The source current is same as the receiving end current because all are in series. 164 into, it is receiving end power factor, it is equal to 0.78. This is equal to 5322 kilowatts. The transmission efficiency equals the receiving end power, it is the load power, it is equal to 5000 kilowatt divided by the sending end power, which is equal to 5322 kilowatt. So this is equal to 93.9%. This is the transmission efficiency.